Hi folks, welcome back to Math with Captain Rod. Purpose of this video is to demonstrate how to use rectangles and sigma notation to estimate area under curves. So what we're going to do here is we're going to look at the curve y equals x cubed plus 3, and we're going to try to estimate the area bound between that curve and the x-axis between x equals 0 and 2. Right, as usual, a picture is a good place to start with this. That curve is looking something like this. And again, I'm just going to do a rough sketch. We're looking out to x equals 2 here. So this part of the curve not really relevant because we're running 0 to 2. I could leave it, but we don't really need it. Okay, so now the idea here is how do we estimate this area in green here, this stuff? And the idea is to break this thing into a bunch of geometries that we know about. Rectangles are the most common. The area of a rectangle is length times width. Now, it's very important to realize that how you set your rectangles up have a dramatic effect on this problem. I'm going to use 4 rectangles. Right? You can choose any number. Typically, the more rectangles you use, the more accurate results. The purpose of this video is just demonstration here, so I'm just going to use 4. And there's different ways I could set those rectangles up. I want to take a minute and talk about the different methods here. One possibility is I could set them up like this. 1, 2, 3, 4. If I set them like that, set these rectangles up like this, it's important to realize there's going to be areas here that are missing. So this is going to give me a lower bound estimate to the area under the curve. Another possibility is I could set these rectangles up like this. 1, 2, 3, 4. And this is going to now include areas here, 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 and here that aren't actually under the curve. So in math we say that that's going to give me an upper bound estimate for the area. Right? Now, what I'm going to do is I'm going to use what's called the midpoint rule. I'm going to draw my rectangles in such a way that the curve goes right through the midpoint. I like to call this the Goldilocks method because this tends to yield results that are basically, not too big, not too small, but just right. Now imagine here, that these are all rectangles of equal width here. Right? Now, the first thing I typically do is calculate the delta x. That's going to be the width of these rectangles, and the delta x is going to equal b minus a over n. This is the upper bound minus lower bound over the number of rectangles. B minus A gives this distance in any of these problems from the lower bound to the upper bound. In this example, that's going to be, 2 minus 0 over 4, which is 0.5. So the width of all of these rectangles is 0.5. I know it doesn't look like it in my picture here. Well, this is just a rough sketch. So imagine 4 rectangles of equal width. Now, the area of each rectangle is given by the function value right at the center of the rectangle. Or I should say the area is length times width, but the length is given by the function value at a very specific x value. The x values we need for our calculations are here, 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 and here. They're the x values at the centers of the rectangles. Because the f of x is, the delta x is 0.5, the first x value we need, this one, is going to be 0.25. Because this is 0.5 from here to here, this is right in the center, so I'm subtracting half of a delta x. The second one we're going to need is right here. Now, from here to here is delta x, 0.5. That makes the second x value 0.75, coming from 0.25 plus 0.5. The third one we're going to need is this guy, and that's going to be this plus another 0.5. So that's going to be, 0.51, that's going to be 1.25. And the last one is here, again at the center of the last rectangle. Now, This is going to be 0.5, 1, 1.5 plus another 0.25, so that's going to be 1.75. Very important to realize where these values are coming from before moving on. They're very specific values. They're the x values we need to calculate the length of each of these rectangles. Now, I'm going to actually write out a little formula here. A1 is going to equal f of x1 times delta x. Area 2 is going to equal f of x2, that's going to give the length of that rectangle, times delta x. Area 3 is going to give us f of x3 times delta x, and so forth. So all I'm going to do is I'm going to write a little formula here. A sub I, the I is standing for the 1, 2, 3, or the 4, is equal to f of x sub I. The x sub I are these values, where I can be 1, 2, 3, or 4, times delta x. This is just a formula that kind of describes how we're going to calculate the areas. The total area we're going to get by summing these up. So in sigma notation, here's what it would look like. Sum from I equals 1 to 4 of f of x sub I times delta x. Now I'm going to go ahead and write out the sum. All right, so the first one, I equals 1. That's going to be f of x1, I'm sorry, which is going to be 0.25 cubed plus 3 times the delta x of 0.5. Next one, for I equals 2, that's going to be f of x2, that's going to be 0.75 cubed plus 3 times delta x of 0.5. I guess I can probably, I'd like to get this in one line if at all possible. Next one, it's going to be f of x3, it's going to be 1.25 cubed plus 3 times 0.5. Last one is going to be f of x4, it's going to be 1.75 cubed plus 3, darn it, times 0.5. Right? So what I have now, what I'm looking at is the sum of all the areas. So this one represents area 1, area 2, area 3, and area 4. And we are summing them all up. That's what the sigma notation means. So I'm not going to take a moment here and let my crew, my motley crew here, calculate a value. One of you guys estimate a value. I'm going to pause this while we wait here. This might take a second. Here, so we're back here, and my helpers here got 19.75. I want to talk a little bit about the actual area under the curve. And again, for those of you in class right now, we're going to talk about how I'm doing this in a day or two. But I can tell you that the actual area under that curve is going to be, give me a moment here, 2 to the third power plus 3 times 2. Whoops, I'm sorry. No, I didn't do that right. It's going to be 2 to the fourth power over 4 plus 3 times 2. That's what it's going to be. So 2 to the fourth is 16 over 4 is 4 plus 6, 10. Whoops, let me make sure I did this right. 2 to the fourth plus 3 times. All right, so we got to go back and take a look at this, because I'm getting 10 out of that. Say what? Did you remember all these 0.5s? Oops, all right, so we got to go back here. It's okay. That's why we check them. I got 10 for the actual exact area under that curve. And what did you get when you estimated this? 9.9. All right, so what we got here was 9.9. Area is approximately 9.9 for our estimate, again, using Goldilocks method here. I think what I'm going to do is just kind of overview this and then end the video. So when estimating area under the curves, what you do is you break the curve up. Usually you're using rectangles, but you can also use other geometries. We're going to talk about how to do this with trapezoids tomorrow. You got to pay particular attention to how your rectangles interact with that curve, whether they touch your rectangle here or in the middle and the left, because it drastically affects your setup. I'm using the midpoint rule, so I set these up so that the curve hits the midpoint of each rectangle. An important thing to realize is you're going to need function values. You're going to need x values at the midpoint of each rectangle. So that's the first thing you have to do is get those values. That's what this stuff is. Then the area is given by the function value times delta x. Then the next one is the function value times delta x, and so forth. Now, the setups can change a little bit. If I had another curve in here, then these equations have to be modified on kind of a case-by-case example. But the basic idea, though, is find the correct x values, write an expression out for the total area. In this case, it's the sum from I equals 1 to 4 of f of x delta x. And then use your x values to calculate areas. Add them up. So I hope this video helps demonstrate how to estimate area under curves. Have a great day.